One, two, one, two. Hello, students. This is a recording that deals with how to put a tool virtually on the HAL robotic system. I start from the tool mount I have given you. So you have a tool mount already, and you are designing a tool that sits on top of it. And I describe how you attach this to the robot, and you will print out your object that you bolt onto your tool mount, and I show you the relationship between doing it virtually on the robot, on the HAL robot, and the the things you need to be aware of when you are working with a physical machine. So I first want to look at where we start from. So we start from our tool mount that sits on top of, on the flange. Yeah, so it sits on the flange, and I have created a very simple tool, a cone, and it also has a point on the top. So how do we attach this onto the robot? The first thing I recommend you, which is probably the easiest way to do it, I would bake everything. So I go to my tool mount and I bake this, and I would bake it here on level 1, and I would bake this one on level 2, no, layer 2, and this one on layer 3. Okay. That my tool sits in the center, and at the moment it sits below the center because I gave you the tool mount that it sort of sits flush on the top of your X and Y, like here, as you remember. So as we have them now physically in our Rhino environment, I select everything and I just put it onto the 0, 0, 0. I press apply. So I have now my tool mount. Let's go and hide this. Let's do this as a shaded. So here, tool mount, a simple tool, in this case a cone, and that is basically what you design and 3D print or laser cut. And I have also included this point, which will be the tool center point, the TCP. So this is basically the data which we give to the robot. So this is where the point, so the point when we do frame movements, so we go from point to point, or this point is the TCP that runs along a curve. Okay, what you can do now, and I think that's probably the easiest way, go back here, I take a B-rep, and I set multiple B-reps, and I choose this one, basically this one, everything that is tool except your TCP. So we have this one now, and I also import the point. I set one point. Okay, and here I internalize the data that it sort of lives. Okay, and I just put this into a group. You can also name this cone tool. So, okay, I have internalized this, and now we open our base station. Where is the base station? Oh, this is the base station already. So I want to go back to my original. And I also, so again, make sure that I have this copied. And I go and open my base station. Here you go. Okay. Now we make it. Yeah, let's do it like this. Okay. Right. So we still have the old tool mount here with the TCP. So here's our setup. And I just copy and paste this in here. So here we have our new tool. This is the old one. Now, as you know, let's hide all this. So hide our preview. And here you see the old, tool mount with the pin that is currently on the robot, but you can also see this new tool. It sits already in the XYZ 0 position. Very, very important. Make sure you do that. So here we've got our mesh, and we can basically just delete this. So when we have our robot, the robot sits in the XYZ 0, and we touch our tool, and we can also delete this. So that's the old. So what do we give our body? This is our tool that hangs in front of our robot, right? We put this also to 0. So what does it ask us? So it wants to have a body, and we give it the body, but it also needs a center and an original point, and that's this one here. So this is our tool center point, this point. We can also give this the original. So as you can see here, we have now a plane that sits on top of our cone, which is associated with our point, right? So we give this an XY plane. Our tool, so with the flange, with the tool mount plus tool, is attached to the body. You can give it a mass, so that means if you have heavy tools, HAL calculates a delay if you have heavy weights, for example. So that's something you need to consider. Okay, we can also rotate our tool, and in this case it doesn't really matter. However, that's perhaps in a second video then. When we have more complicated tools, or I can show you I'm currently working on. This is a fairly simple setup. You have a tool mount, a tool that just goes straight up in the XY plane and points upwards. HAL always puts this straight onto the robot flange, and it operates it downwards. So let's have a look how this sort of materializes if we recalculate this and we visualize it in our simulation. So we've got our robot. And here you can see it is attached to our robot. I'm not quite sure what we have. Here, this is still the exercise, a point movement, where we go to our calibration point downwards. Okay. When you touch the tool, the first thing you should do is perhaps you do a simple frame movement. which we have here. So we have a frame movement, you have this code, you give it a few points. In this case, we move it to the pin, the calibration pin here, to the center point here, which are these 2 points. So this is the point here on the rotating table. This is the calibration pin on the tool rack. And we feed this into our frame, so movement by frame. When you touch a tool, you will, and it kind of depends where the TCP ends up. If it's a similar tool to what you replace it with, you probably don't get any warnings. But if the tool is more complicated, then the TCP doesn't necessarily, so if this is your TCP, it doesn't matter. But let's say you have an object. You have an object that sits on your TCP in this direction. So your TCP sits offset and the plane is in this direction. It gets a little bit more complicated. And there are a few things you need to then work with. So, and it's always good to start with a home position. If you do the simulation and you get a lot of red flashes on the robot, I would always start going back to your home position when you set the home position to 0, 0, 0. It's also useful to do your X and Y and the rotation, set everything to 0 and work from there. So let's see how is our simulation here. We've quite a strong rotation here, as you can see. I stop this now. And if you go, you see the rotation here is quite strong. I think we can do this simpler because we have our feeding cables, our air and data cables that go to the head. So let's see whether we can simplify this. And it could be the direction of the TCP. So I would rotate this by 180 degrees to start with, recalculate, and let's see what it does now. And you can see our ABB robot is not rotating anymore here. So this is a very simple way to prevent strong rotation on your arm. This last movement was just a flick back to the 0 position, and we could prevent the flicking if we just go and add the 0 position there. It goes back down to our 0 position, it should go up. So I think that flick doesn't really mean much. It doesn't, that shouldn't do anything. But we could also, let's see, if we move this a little bit downwards, the home position, 40, 30, that's minus 30. Well, it's this one, no. Sometimes you need to play around with it a little bit to kind of figure out. I don't quite know. So yeah, this is a better starting point. So we have the home position closer to these points. Yeah, so you have less of a movement. Try to avoid a lot of movement to points. So you want to get close to your starting point. We could also move the rotating, so the joint 1 is this 45. Oh no, it's not there, so it's minus 45. I just want to get the starting, the home position in between the, so we start somewhere from here, downwards, up, downwards, upwards. It should go somewhere here. There you go. Yeah, so that flicker doesn't really mean much. So we can actually do this. And then so the simulation was just in a loop, so that's why it's a flicked, but it wasn't, that wasn't really what the robot did. So it just does one, so you can loop the animation here, the HAL simulation, or not loop. I would not loop it, so you go just through, it just shows this one setting, home position, frame movement, back to home position. And then you see how the code runs. Okay, so let's have a quick look at a slightly more complicated setup. I was working on, I have a smaller robot, you might see it there in the background. I have a small IRB 1200. It's the milling, it's here. So let's have a look. So I have a little milling, well, I'm still working on it. So I designed this entire thing for my small robot. I want to do like a small milling station. So I have a small spindle, and I need to build all of this. So this is a bracket that came with a mill, but I have to build this flange. So that's this one. Let's quickly hide this. But you can see it there. So let's visualize that. That's the spindle, and the tool mount plus flange, right? And I have also set a point here, and I did offset that point a little bit because this will also have this milling tool will also have yes. So and here you can see the tool, the flange sits 0, 0 in the XY position, but the milling tool sits sideways into the X direction, and the TCP sits here. And I had to play a long time around to figure out the right position, that the spindle doesn't hit the robot and it doesn't work, and that I have no distortions. It took me a long time. Sometimes when you have complicated setups like this, so where your TCP sits to the right of the center of your axis and of your flange, where you mount it onto the tool. So that is a little bit of a fiddle. But yeah, you can figure it out. It's basically, as long as you, and that's the great thing with HAL, we can just test things endlessly in the simulation until everything is sorted out. And here I have a little milling surface simulated. I'm kind of working on, and you can see the TCP sits slightly on top of the spindle. So it's quite a heavy code. And is it working? Yes. So this is the approach. So I wanted the spindle to kind of sit in this way. Yeah, this is a small spindle, and this is only for milling fairly sort of soft materials like hard foam and perhaps very soft wood on small scale. But it's also, I want to get into milling on our larger IIB at the campus. So this is a good test setup to figure out how milling works. And there we will also have to have another software that generates tool paths for meshes, for example. So this is sort of advanced robotic, six-axis robotics. So we will do simple milling later this year. Okay, so quickly recap. Make sure that you prepare your B-rep, so you can either use a B-rep or you can even use a mesh. Just make sure that these meshes are small. Meshes tend to be data heavy. That's why I like to work with B-reps. This entire spindle is 17 kilobytes small. It's tiny. So I'm always make sure that I have small data points to import here, because you do not want to have like a lot of simulation with heavy meshes that hang off your robot. It's not necessary. So make sure that you prepare your B-rep and place it in the XY0. Import the TCP point where you want and the plane, in which direction the plane is. We will talk about planes in class. It's a little bit more, advanced, or you need to start thinking about where the planes sit in relation to your TCP. But that's pretty much it. So the only thing then you need to figure out is, once you have your tool on the robot, you also need, once you have touched it, you have your simulation, you do a simple point-to-point movement from A to B. And then you need to see whether actually the robot replicates what you actually have in your simulation. Your simulation might be wrong, so you might have to change your simulation, that you actually on the robot see what you execute. Yeah, but that's something we will also discuss in class. Okay.